Hello. This is the Michael Nielsen talk, Hacking the Future of Science. We're just letting a few stragglers come in. I'm Big Kate, I'm the Herald. We're going to try and have questions at the end. Questions at the end or questions through? Questions at the end. There should be a microphone going around to you so you can talk into the microphone so that everyone can hear. Michael is... Well, let's be honest, he's just flown in from Canada to be here. He had to go through so much stuff to get here. He's one of the fathers of quantum computing. Probably one of the leading lights here. If you want to read about him, go read him on his blog. He's got tons and tons of stuff about this man. 50 lectures of papers. He's talking about the future of science here. This is part of the people and the politics track. So we're talking, this follows on from WikiLeaks. It's moving on to stuff about hacking in the thing in Zone 2. And I think that's about it. I think it's up for you now.
How's the mic? Higher? Okay, is that better? Well, hello everybody. It's great to be here. I was surprised by the invitation and absolutely delighted. It's the first time I've been to one of these events. I'm going to start with a slightly silly question. The question is this: how many people here regularly read blogs? Please just raise your hand. Okay, so maybe a better question is, how many people don't regularly read blogs? Ha 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 ha. Okay, how many people here run a blog? I think there's some confused people. So when I ask scientists that, well, I don't ask exactly that series of questions, but basically that series of questions, I tend to get very different answers. In particular, blogs, wikis, open source ideas are looked down on by many scientists, or they're just not interested, or they're not aware. But over the last few years, that's been starting to change, and some ideas, I guess, from the open source community about open sharing of materials using online media are starting to change the way in which scientists work. So what I want to do today is give you a small taste of, in my opinion, some of the most exciting things that are currently going on. There are quite some considerable parallels to open source. I should sort of warn you in advance that in many ways scientists are a long way behind in their use of online media. And there are also some interesting differences, which is perhaps the most interesting aspect, and certainly there's much still to be done by the scientists. So I want to start with something very specific and concrete. I want to talk about a very unusual blog. This is I say a blog, but you, well, bear with me. It's pretty different. It's very unusual if you're not a mathematician. It's the blog shown here. It's probably not that easy to see. It's a blog called What's New, and it's run by this guy. His name is Terry Tao. He's a mathematician. He won the Fields Medal in 2006. So this is a prize in mathematics. I guess it's often called the Nobel Prize of Mathematics. That's maybe a little bit unfair to the Fields Medal. It's only awarded once every 4 years, so it's actually considerably harder to get. He's known for many, many different things, probably the most famous for something called the Green-Tau theorem. This is his collaborator, Ben Green. And what they proved, it doesn't matter what they proved, but basically there are arbitrarily long arithmetic progressions of prime numbers, so primes which are evenly spaced apart. They proved that, I guess, 2 years ago. So he's a blogger, and he posted 118 posts last year. I think he'll probably exceed that this year. You can get some idea of the quality of the posts from the fact that last year's posts were issued as a 2-volume set by the American Mathematical Society just a few weeks ago, and the 2007 posts, which was the first year he started, were also published by the American Mathematical Society. So this is not a guy who's sharing cat pictures with his mathematician buddies. He's doing something rather different to that. And what I want to do, I want to focus really, really narrowly, this is kind of, through the eye of the needle, on a particular blog post. You might suspect me of cherry-picking my examples here a bit. I kind of am, but there are a lot of posts that are like this. So it's a post titled, "Why Global Irregularity for Navier-Stokes is Hard." Don't worry if that doesn't mean anything to you. It's basically a post about waves, in some sense, or in particular a set of equations from the 19th century, the Navier-Stokes equations, which describe wave behaviour. So you're not going to need to know anything about the Navier-Stokes equations. That's not the point of the talk. The point that I want you to understand here, they're renowned as being very difficult to understand equations. So Richard Feynman spent a fair fraction of his career working on the equations, or several years, and made little progress. Some of the other great physicists and mathematicians, Lev Landau and Kolmogorov, spent a large fraction of their career and had very limited success in understanding very much about waves. And one of the big Clay Millennium Prize problems in mathematics, these are the $1 million prize problems, 7 prize problems, sort of the biggest problems in mathematics, is basically to better understand these equations. So what Tao's blog post was about was basically that particular problem. So what does it contain? Well, it's not a talk about the Navier-Stokes equation, so let me just give you the flavour. It starts with a brief explanation of exactly what the problem is. It tells you that in 2 dimensions, we actually understand wave behaviour incredibly well, which is something I didn't know before starting, and says, why is it so much harder in 3 dimensions? And it says, well, there's a standard answer to this, which is that turbulence is really difficult to understand. Okay, but he says, well, that's the standard answer. That's what everybody says. Oh, turbulence, that's what makes fluids, waves difficult to understand. He says, well, what does that really mean? And he gives an alternate explanation in terms of something he calls supercriticality. And he explains what this means. He says it means you have invariance to control the behaviour at all length scales. And what that kind of means is that you have some control. You understand things like energy density locally, which control the behaviour at very small length scales. So the conventional problem people talk about with turbulence is that even while it's regular on long length scales, it gets really, really complicated when you look down low. So he's sort of phrasing that in a much more mathematical kind of a language. He talks about the known invariants, which can control it, and how they get weaker at shorter length scales. He summarises the 3 known broad strategies of attack for proving these kinds of results, and says supercriticality is a problem, severe problem for all of them. Okay, we're still going through the same blog post. I need to speed it up. There's a lot more still in it. He talks about the known invariants. He surveys and critiques all the known attempts on the problem, the Clay Prize problem. Says there are basically 6 ways of attacking it, or describes 6 ways of attacking the problem. The post is absolutely full of clever perspectives, insightful observations, and clever ideas. Basically, if you're a mathematician, or for that matter a physicist, which is my background, it's like having a chat with an absolutely outstanding mathematician who's willing to share their best thinking with you. This is, it's not a typical boing-boing post, to put it mildly. After the end of the post, there are then 89 comments. Actually, there were 89 comments when I last counted. I think they're now up to more like 120. And there are a whole bunch of sort of top-notch mathematicians in their own right chiming in, batting ideas backwards and forwards, and sharing insights of their own. The conversation also spread out to other mathematical blogs. That's one blog post. Okay, I've gone on at some length about this. The reason why is I want to give you some idea of sort of how overwhelming it is. There's a lot of these posts. There are 118, not all of such high quality, of course. There's a famous instance a few years ago you might have heard about this Russian mathematician, Grisha Perelman. He won, it's a famous recluse. he proved a century-old conjecture due to Poincare. And it's incredibly difficult, this proof of his, and he didn't really publish a full proof. But Tao, on his blog, through 19 separate posts, gave an outline proof of the Poincare conjecture following this up. Okay, that's one person. Tim Gowers is another Fields medalist at Cambridge University. Funnily enough, he also runs a blog, and he's got all sorts of interesting posts on his blog. We have Elaine Kahn, another Fields medalist. He also runs a blog. We have Richard Borcherds, another Fields medalist at Berkeley. Well, he runs a blog, but like so many bloggers, he got sick of it, and this is the last post. It's from January 2008. So that's kind of too bad. Anyway, the basic point here is that of the 42 living Fields medalists, roughly 10% of them have blogs. So a few years ago, this was something that scientists were not interested in as a general rule, embarrassingly, in my opinion, because people have been using these, online media of all kinds very effectively for years. I've concentrated on Fields medalists, I guess, just because they're the best, and I wanted to sort of give you some insight into how things are at the top there. It's obviously spreading, but of course there are many other blogs. So from a scientist's point of view, not sort of a general point of view, blogging has many interesting characteristics. It's informal, it's rapid fire, and in particular it's a way of sharing insights that would be very difficult to publish in a conventional way. So you can take sort of the small but striking ideas that you have as a scientist, the sort of stuff that you can't publish in a conventional sort of a form, or thoughts on general approach to a problem. These things are too small to be published, but very often that's really that's the key point. A friend of mine once commented that basically what a paper is you sit there in the cafe, you have a really clever idea at some point on the back of an envelope, you translate that into a 40-page paper, it's disseminated around the world. Other people take the paper to the cafe, they read it, and if they're lucky, eventually they figure out what was on the envelope. And in some sense, this is sort of giving you more direct access to the envelope, so to speak. It's also, more importantly, because you can publish these small insights that contain the seeds of later progress. I mean, that's very important. This fact that there are all these people participating in this conversation who ordinarily would not be, it's a way, in a sense, of scaling up scientific conversation so it becomes widely distributed both in space and also, in some ways more importantly, in time. So that the kind of conversation that usually takes place inside sort of the hallway or the lecture room or the classroom instead starts to spread out so that it's taking place all over the world. And you know, not only is it broadcast, but of course people can contribute their best insights back. It's also really critically a difference from conversation is that it's making scientific conversation searchable. Those of you who run blogs probably, well, like myself, have a tendency to Google yourself for something that you kind of half remember but don't quite. But here, you know, it's really critical to be able to go back to some of these insights and find where people said what. If you Google Navier-Stokes problem, you discover that Tao's post is the third hit, or depending on where exactly you Google from in the world. So it makes it very easy for future mathematicians to benefit from it. You know, a curmudgeon might say, shouldn't the best papers be at the top of the Google rankings? And they kind of have a point, but really if Google is doing its job, then the ranking should reflect the significance of the item, regardless of what format it is. It doesn't matter whether it's paper, a blog post, or some other form, and certainly this blog post is an awful lot more useful than most papers on the subject. So I think it sort of deserves its ranking. You know, from a scientist's point of view, a good conversation with an insightful colleague is certainly worth more often than reading even the best of the papers. So as search engines, I think the right thing to say is that as search engines become better personalised, search results should better reflect your interests, and so you should, if you need to see it third, you'll see it third, and if you're the kind of person who needs to see it 20th, you'll see it 20th. So I've talked a lot about Tao's blog in particular. I guess I've been reading and some blogs for more than 10 years, I guess, or so. Something that really drove home to me, though, was the fact that we tend to think of blogging as a fairly fixed medium, not completely fixed, of course. But what he's doing was, and all of these people, they're expanding the range of the blog medium simply through their own creative insight. They're not adding to the tools. They're simply thinking of new things which could do. Nobody realised that you could sort of essentially start your own amazing journal in this kind of way before he started to do this in 2007. They're just taking existing tools and using them in new ways. It's also interesting, of course, to talk about adding new capabilities to the existing tools. Actually, a critical fact, and a really interesting fact, is that a developer at WordPress.com, Michael Adams, in 2007, added the ability to do LaTeX on WordPress, basically as a joke. He says in his blog post announcing it, I'm sure that sort of me and 3 others will be interested in this. And yet it's enabled this explosion. So something that he did apparently as a sort of a very minor thing has really had a big impact. There are many other things that could easily be added to these tools which aren't yet there. Basically these dots here, that's another talk, well actually it's several more talks about things that would be interesting to do, which I'm not going to talk about. So I've started with blogs. I want to talk about some other things. I mean, that's a very familiar kind of a thing. I've started with the familiar. In particular, I want to talk a little bit about open source biology and the Registry of Standard Biological Parts. How many people are familiar with open source biology? Okay. All right. So what the Registry of Standard Biological Parts is basically it's SourceForge for biology, or GitHub, or whatever your favourite place is. The reason, or the sense in which that's true, is that if you want to specify a living being, the way you do it is by specifying, in some sense, the DNA sequence, right? And that's digital. And so you can sequence your organism, and you can upload the sequence to an online repository and share it. And it really does function in many ways quite a bit like SourceForge. So there's a catalogue with all sorts of different categories. There are, at the moment, something like 3,200 biological parts. So when I say biological part, I just mean a DNA sequence of some kind, contributed by more than 100 groups. Depends a little bit on how you count these things, but those are kind of ballpark figures. And you can just go through and search, and there's all kinds of information and annotation available. But one of the most the most significant single thing, I mean, you click through, and what you get is this, TTATGACAA, blah, 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 blah. What does that mean? It's the DNA base pairs. And what you can do, in principle, and people do this, is you can download it. You can synthesize the life form. Actually, typically people don't do that in their own labs. They send away. You can do it. It depends on the length, but you can do it. If it's not too long, you can do it. I think it's 50 cents a base pair at the moment. But the virus is 10,000 base pairs. So, whatever, that's $5,000. It's not that much money. So you can, if you like, improve and alter that life form, and you can upload the result. And people do it. A lot. I mean, a surprising amount. I should mention, this is kind of an aside, but it's kind of hard to put these things together, or a priori it's hard to put these things together. So there's all kinds of interesting sort of thinking and about standardization to make it easier to combine parts. I don't really understand all that so well, but it's an important problem. I'll just give you an example. They run a competition called iGEM every year where what they actually do, it's interesting. By having this kind of open source approach, it makes it very easy to get into biology because you can reuse what everybody else has done, and you're sort of starting from that point. And so they run a competition where they bring undergraduates from around the world to MIT called iGEM. And, well, basically, there's a big prize that goes to whoever synthesizes the coolest thing. So last year there was a team from Slovenia, and just to give you this is sort of just an example. There are dozens or hundreds of interesting projects. They found a vaccine against this bacteria, which is apparently, I am told, found in roughly half the world's population. In most people, it doesn't have any effect, but apparently under sort of the right conditions or the wrong conditions, depending on how you look at it, it can make people susceptible to ulcers and apparently also to some forms of cancer. So it's not something that can be deployed. It's not like it's gone through the FDA or whatever, but it's certainly an interesting sort of start down that process, and they contribute these parts back to the registry. I should say, so even while these sort of sequences are getting uploaded to this registry, in fact, much of the development work is also taking place in the open because of a parallel development, which is called Open Wetware. And basically what Open Wetware, it started out as MediaWiki, and they've added a whole lot of custom features. They've added some blogging and a bunch of other bits and pieces. It's quite highly customized. And a lot of the groups who are doing this open source synthetic biology are using Open Wetware as a platform for their work. So this is just an example that Peking University actually has been one of the more active iGEM groups, and they have a great set of pages. They do all kinds of stuff. I guess the thing that I enjoy the most in some ways is the brainstorming. So if you go through a lot of the groups, they do brainstorming about what sort of things they want to do. And so you don't sort of see the full thing here. So here's their first idea, which is E. coli to decompose polluted water and sludge, and then there's a link to a PowerPoint file which describes it in much more detail. And you keep sort of going down, and they have all these ideas, and finally they pick one. There's all kinds of stuff like that done there. So essentially what they're doing is they're building an online biological commons with the goal of engineering synthetic biological systems using standard biological parts. And maybe one day, eventually, they'll be able to do, as people do in programming languages, they'll be able to build multiple layers of abstraction. So instead of having to work at the DNA level, sort of the assembly code level, you'll be able to move to higher levels. I think that's a pretty exciting kind of a prospect. Okay, so that's open source biology. I want to talk a little bit, just briefly, about Open Notebook Science, which is another development. It's kind of the most radical in some ways. So the Open Notebook scientists are people who are systematically attempting to put all of their ideas, scientific ideas, online. They're trying to systematically put all of their data, experimental data, online in as close to real time as possible. I should have said that. That's true also of the ideas. And they're also trying to provide ways then of filtering that, because that's an awful lot of information. It's no good if it's not actually organised in some useful way. So, it's really the fundamental principle here is that the best way to create value in science is to make it easy for others to improve your work, and they can't improve your work if you're not actually sharing it with them. So I'll give you just a few examples. Somebody, in some ways, he's a pioneer of Open Notebook Science, although he didn't call it that, is Garrett Lacey. Garrett's a theoretical physicist. If that name looks familiar, it's not entirely surprising. Garrett actually, I guess a couple of years ago, there was a lot of fuss about Surfer Dude discovers theory of everything. I don't know if any of you remember that, but that's actually Garrett, whose name I have misspelled. Horrible. Missing a T. Anyway, the Surfer Dude discovers theory of everything aside, he's a theoretical physicist, a perfectly normal one. And one of the interesting things that he's done for several years, is he's maintained this wiki where he just, as he works through stuff, he uploads it to the wiki. You can sort of see him working through, he's understanding all these different topics, he's brainstorming ideas and so on and so forth. Garrett has called it My Brain Online. So that's sort of one example. There's a chemist, Jean-Claude Bradley, who actually coined the term Open Notebook Science and has been one of the people who's really systematically sort of pursued the idea and developed it. And so this is his useful chemistry page, it links to all kinds of different things. So there's a blog, there's a mailing list, there's a molecules blog with all sorts of different ways of searching through it. You just kind of keep on going. They have their experimental plans. They have, you can just, the amount of information that they're putting online is quite amazing, and they're finding ways to federate it in ways which are useful for other people. It's quite interesting, actually, to go through and see what Google searches come up most frequently. You'd be surprised. There are some complicated molecules whose names I can't pronounce, which are surprisingly frequently searched. Cameron Nalon is another person who's doing it, also a chemist. So they're experimenting with ideas like lab equipment that automatically posts to the web. In fact, they're very interested in things like robots that do experiments. The reason why it's interesting to have robots that do experiments is because you can then open source the code that's used to control the robot, or you can, in fact, open source the description, the hardware as well, potentially. So you can really make your experiment very reproducible in this way and very, very open. They're very interested in things like machine-readable data, which should enable data mining and all kinds of automated inference one day. That, by the way, I should say that at least certainly my sense is that this kind of idea of making data machine-readable and then doing automated inference has a bit of a bad name. This idea of the semantic web has been around for a long time, and a lot of people poo-poo the idea. Science is very interesting in that you have these small communities of people who are doing these things and who are willing in some ways to get together and agree on standards, which is, I think, what's necessary to make this kind of automated inference in a network eventually feasible. Okay, so basically, sort of to sum up this part of the talk, or the first 3/4 of the talk, blogs, open notebooks and so on enable filtered access to new information sources and new conversation. In a sense, they form a collective short-term working memory for groups of scientists, a conversational commons for the rapid collaborative development of ideas. The way I like to think about it is that, in some sense, what these things are doing is they're restructuring expert attention. So what do I mean by that? I just mean, if you look in Tao's blog comments, the very first one, actually, on that Navier-Stokes post, I'll just give you an example, is from a very well-known mathematician named Greg Kuperberg. So Greg Kuperberg knows nothing at all about the Navier-Stokes equations. That's the first thing he says. I know nothing about this, but blah, 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 his thoughts. And then this conversation gets struck up, and Kuperberg has some very interesting things to say, and it stimulates Tao and so on, back and forth. So here are two people who are engaging in sort of a mutually beneficial interaction that otherwise wouldn't have happened. It's a very small example, but when it's extremely good scientists like that, it's very significant. The reason it's significant is because, in some sense, expert attention is the ultimate scarce resource in science. What I mean by that is, scientists complain they don't have enough money, they don't have enough experimental equipment, they don't have enough this, that. But you can have all the money in the world, and if you're stupid, it just doesn't help as a scientist. But if you don't have much resources and you're very clever, you can do amazing things. It's true that expert attention is it's the key bottleneck. And the more efficiently it can be allocated, the faster science will progress. So what I'm talking about is ways of more efficiently allocating expert attention. So I'm going to sort of finish, my last example anyway, is a completely different way of thinking about the reallocation of expert attention. It starts with the idea of markets, and at least a very common belief is that markets are an excellent way to efficiently allocate scarce resources. How many people here would describe themselves as pro-market? Just out of curiosity. Okay, not many. So, just a quick anecdote. It's from Paul Seabright, who's an economist. Just after the fall of the Soviet Union, somebody visited Seabright in London. It was a very senior official from the former Soviet government, and the question, basically they went backwards and forwards. He was visiting Seabright to talk about setting up a market system in Russia, And they went backwards and forwards, just talking about food and various other things. And the official finally said, look, we really want to understand what the market is, but I just don't. Can you please tell me who is in charge of the supply of bread to London? And as Seabright says, the fact that nobody is in charge of the supply of bread to London is an astonishing fact. As many as the failures of markets are, they do a pretty reasonable job of allocating certain types of resources. Anyway, let's explore the idea that maybe we can create a market for this resource of expert attention. So we'll talk about an online market in expert attention run by a little company called Incentive. I need to start most of the way around the world in India with a not-for-profit organisation called the Asset India Foundation. And what it does involves some of the 2 million women involved in prostitution in India. And basically it helps girls, typically daughters of prostitutes most frequently, some sons as well. It helps them escape from the sex trade. And the way it does that is by providing training in technology. So they've so far set up 5 training centres throughout India where they've trained several hundred of these girls and placed them with technology companies. And apparently they get an awful lot of requests from local governments, local town level, to set up more of these. They have a problem, though, which is that in many of the towns requesting them, they don't have very reliable supply of electricity. And if you're doing technology training, that's a bit of a problem. So one of the problems that they had was in trying to get wireless routers. In particular, they wanted low-cost, solar-powered wireless routers. And they took a look around. There are a bunch of solutions which are available, but what they specifically needed in their particular situation didn't yet exist. So most of the way around the world, you have in Boston, just outside Boston, the town of Waltham, you have the company Incentive with their online market in expert attention. So what that means is that companies like Eli Lilly, Procter & Gamble, and I think it's about 80 others now, can pose on this site what are called challenges. And what a challenge is it's a scientific research problem together with a prize for solution. So it's a very well specified scientific research problem. You probably won't be able to see this, unfortunately, with the lighting, but that I've sort of put an example up here. It's one of their prizes. It's a prize for finding a biomarker for motor neuron disease. It has a $1 million prize, which is that's high. Typically their prizes are tens of thousands of dollars, some are hundreds of thousands of dollars. $1 million is definitely on the high side. So they have 160,000 people signed up for the site in 175 countries. They've had so far 200 plus challenges have been solved. What's this got to do with Asset India, the organisation I was talking about before? Well, Asset took their problem, they got in touch with the Rockefeller Foundation, and they said, we need a low-cost solar-powered wireless router to expand what we're doing. Rockefeller, in turn, got in touch with Incentive and said, we'll put up $20,000 in prize money for a good design for this, one that meets all of their requirements. They broadcast that out to the rest of the world. 400 people downloaded the challenge. That doesn't sound like very many, but actually to download a full description of the challenge, you have to go through some hoops, so it's a reasonable number. 27 of those people submitted solutions, including one from this guy, Zachary Brown. He's a 31-year-old software engineer from Texas. He's the person who won the prize. He got the $20,000, and Asset got their design for low-cost solar-powered wireless router. Now, what's interesting about Zachary Brown is his characteristics. This is a guy, so he's a software engineer, very interested in open source, which is one of the things that to keep everything low cost, Asset strongly designed in the design. His hobbies were wireless radio and solar power on top of that. Right? He was, at the time, he was basically transitioning, he was changing his home office. He had a plan to change his home office completely over to being operated under solar power, and he was going to do all the the modifications necessary. So he was kind of, he was the right guy to be talking to. And that's the advantage of having 170,000 or 60,000 people to be broadcast to. I should say there's sort of a nice, happy coda to this story, which is that it's now being prototyped at the University of Arizona, the design. So I've been very enthusiastic about all these new ways of doing science. A skeptic might say, many skeptics do say, aren't all these new forms of contribution just a distraction? As a scientist, should you blog when you could instead be writing papers? Should you contribute to Wikipedia when you could be writing grants? So why? Well, actually, let me stop and just talk a little bit about this point. Should you contribute to Wikipedia when you should be writing grants? It's really interesting to me. If you look, Wikipedia's mission statement is quite inspiring in a number of ways. To put all the world's information online. It reads in some ways like it was written by a scientist, or at least according to the values that many scientists claim to espouse. But of course there was very little involvement, relatively speaking, from the mandarins of the scientific establishment early on. I find that interesting. Of course the reason is very obvious. You can't list Wikipedia contributions on your next grant application. These seem, if you're not a scientist, these kinds of things seem pretty stupid as barriers, and yet they're enormous barriers to any form of sort of new contribution. So why should you share your ideas, as the Open Notebook scientists are doing, when other people might build on your ideas without giving you credit? So in the short term, these are all important questions for scientists, but in the long term I'm very hopeful. Very hopeful for a couple of reasons. First of all, of course, it's primarily a social problem, getting people to be more adventurous with using these new ways of generating knowledge and of exploring ideas. And because it's a social problem, one naturally expects it to take, certainly probably on the order of decades. Danny Hillis, the supercomputer pioneer, has said something I like very much, which is that there's an awful lot of problems which are just completely impossible if you think about them on a 5-year timescale, and yet which are trivial when you think about them on a 50-year timescale. And I think this is an example of such a problem, getting scientists to be more adventurous. There's also a parallel in sort of early scientific history, which I'll explain through a story. It's a story of Galileo and his discovery of the rings of Saturn. I'll get to that. He didn't actually quite discover the rings of Saturn, but he's co-credited. And so he saw these rings in his telescope, and you might wonder, did he share the discovery in any way? Well, there were no journals at the time, so he couldn't write up the discovery and send it off. And in fact, he didn't. He rather emphatically didn't. To him, that kind of sharing was unimaginable at the time. Instead, he sent an anagram to Kepler, his great rival at the time. Here it is. If you can decode that, you're doing well. And if you unscramble it, what it says is, I have discovered Saturn three-formed. So I said before that actually Galileo was not the guy who really discovered the rings of Saturn. That was actually Huygens some decades later. He did discover that Saturn looks very strange. It has 2 bumps on each side if you look at it in a not very good telescope. And what was later realised is that was actually the rings. So what this anagram business did was it enabled Galileo to claim priority if somebody should later make the same discovery without revealing the discovery. Galileo did this multiple times. So did, Huygens did it, Hooke did it. Newton did much worse things than this. This would have been comparatively good behaviour for Newton in some ways. So, in some sense, he couldn't conceive of a world in which it made sense for him to freely share his discoveries. The first journals didn't appear until more than 20 years after Galileo's death. That was the mechanism that people came up with that encouraged scientists to share their discoveries. But even then, it took decades to establish themselves as a legitimate means of sharing discoveries. The editor, Henry Oldenburg, used to engage in all kinds of terrible behaviour, inciting people to publish, because nobody was interested in publishing in his journal. But what he would do is he actually did this with Newton and Leibniz. He would write to Leibniz and say, Newton has been telling me about his calculus. This is what he's told me. And then Leibniz would be incited and he would write back and he'd add a little bit more. And then he would write to Newton and he would say, Leibniz told me this, and backwards and forwards. And actually the reason why Newton and Leibniz quarrelled over the calculus is because Oldenburg died in the middle of that exchange of letters. Or you can make a pretty good case for that. It's a bit of an aside, but it's one I really like. So there's a real parallel to online media today. Journals were not respectable early on, in the same way as things like wikis are not for scientists today. We have this strange situation where theorists like myself hoard clever observations and questions, the sort of insights that might one day mature into a full-fledged paper. Experimentalists hoard data. We can't conceive today of a world in which it makes sense to share all of that information. As I said before, I think over the short term things will change only slowly, but that over the long term the advantages of moving to the new system will compel change. I have some detailed thoughts on that. Just to finish, I'd like to finish a little quickly. These ideas aren't the end of online innovation for science. They're just a beginning. And far more tools, of course, will be developed. We're going to scale up scientific conversation over the next sort of few years. We'll scale up scientific collaboration. We'll build this collective short-term working memory that I described before and change the architecture of expert attention. Thank you all very much for your attention.
Thanks for the nice talk, Michael. I have a question. As you mentioned before, this is not a technical problem so far. It's more a social problem that scientists adapt to this new way of communicating science. And basically coming back to the roots of the mission of the scientist to spread scientific or to spread knowledge in general. I think we are pretty slow with adapting this. The different scientific communities have a different pace of adapting this. But what is your personal opinion? How can we increase the speed of the adaptation? Do we have to teach students at school, use this stuff, use wikis and so on for communicating your science? Or how do we have to wait until the dinosaurs who give the grants and so on are dying out? What is your strategy that you would propose to increase the speed of adaptation?
Okay. Did everybody get the question? Okay, lots of nodding heads. Good. There are two groups of people who seem to be really good target groups. One is people. So the iGEM is a really good example. You have a whole bunch of undergraduates and high school students actually are getting involved now who are doing really interesting things, in some cases better than the commercial companies. They've written a whole bunch of papers from this competition. And it's not ingrained in them that you keep stuff secret. And so they just collaborate in the open, somewhat in the open. You see some interesting sort of secretive behaviours emerging, but not nearly as secretive as scientists generally are. So that's one place to start. The other place to start, which is I think very interesting, is people at Tau's level or at Gower's level or whatever. They don't have anything to lose. In fact, they're just... scientists at that level, they're not worried about whether they're going to get their next grant. They're not worried about getting a job. And so they're in an interesting and unique place where if they want to be daring and imaginative, they're able to. I shouldn't sort of undersell. I mean, it takes a lot of daring and imagination still to do the kind of things that they're doing, but I do think they're well placed to do it. With all that said, I mean, it just takes a few people. It's really interesting to watch the way the mathematical blogosphere has just exploded. It didn't exist, sort of 2.5 years ago. And now it seems like every day or every couple of days I see another really good mathematical blog. So it's just kind of expanding. And I think that's what happens when you just have a few people really courageously kind of lead the way. An example in sort of the open source community in some ways, there are a couple of flagship projects. I mean, the fact that Linux really took off in the early 90s That got me interested, I guess, in open source whenever, probably by sort of 95. Just a few successes.
You seem very cheerful and optimistic about this, but as someone who works on malware and bad guys on the internet, I remember when we thought the internet would bring out the best in all of us, and interesting how it hasn't quite happened that way. So what do you think about gray goo and evil geniuses and that cluster of bad possibilities?
Yeah. So if I can sort of broaden the question, what do you do about internet trolls of all types, whether they're organised or just doing it for kicks or whatever? And of course, it's a great question. If you have a completely open forum, it's difficult to defend against that. And so the natural kind of thing to do, you're trying to balance between the sort of openness that's necessary for these large-scale collaborations to occur against the damaging effects. I personally, so when you're talking about malware, of course, well, what do I want to say? Okay, so actually, that's a really good concrete example. So what do you do about people who decide that they want to use some of these parts to synthesize something which is really dangerous? And the honest answer, as far as I can tell, I'm not an open source biologist. I watch this, that particular stuff, is that they're not sure. It is interesting that the leading people like Drew Endy is certainly one in open source biology, think a lot about that. They have sensible sounding things to say, but I suspect that the community is not yet large enough of people doing this. It's on the order of hundreds or thousands of people. Once you really, I want to see it tested. If you have tens of thousands or hundreds of thousands of people doing it, they have this DIY bio, which is basically sort of doing it in your garage because it's cheap enough you can do it in your garage. Once that's not sort of a few dozen people in the Bay Area and in Boston, but is rather thousands or tens of thousands of people around the world, what we'll actually see, I don't know. So it's a really good question.
And they all dump it down the sink and float to bed.
Yeah,
Psychologists have identified a phenomenon they call crowding out, where if you have a community of people voluntarily contributing to some kind of commons, and then you introduce a system of incentives to make some contributions to the commons, it tends to kill off other contributions that aren't specifically the ones that are rewarded. And so I guess the question that leads to is, what does a tenure and promotion system look like if it's going to exist alongside this very low-level open kind of collaboration, and does it even make sense? Like, could we have a tenure and promotion system alongside, an environment where all your basic ideas get posted on a wiki and then pursued by other people?
Okay, I'm not sure that question was necessarily audible to everybody. I'll take the liberty of repeating it, which is, what happens to the tenure and promotion system for academics under this kind of environment? Is that a fair paraphrase? There are two separate things I think to say here. One is, at the very top level, people are assessed in very sort of non-standard ways. So actually a good example is Perelman and this proof of the Poincare conjecture, which he didn't submit for publication anywhere, he didn't do anything like that, and he was awarded and refused, in fact, the Fields Medal for that. So they couldn't care less in what format it came. If he'd sort of sent it on postcards from Russia, that would have been okay if it had been a good proof. But of course, it's sort of industrialized. You have this sort of scientific industrial complex at tens of thousands of institutions all over the world, or many thousands of institutions all over the world, and they don't do things in that kind of one-off way where they deeply assess people's work. Instead, there's a lot of sort of bean counting tends to go on. How many citations does the person have? These kinds of things, and of course, that potentially changes here, and you have a lag in time. So there are people writing wonderful blog posts do they necessarily get credit for it? This is sort of the type of question what you're interested in. The only thing that can be done there, in some sense, is to wait to see people start to catch up. So organisations like the Public Library of Science are very aggressively exploring the idea of starting to provide in a systematic way, we're at time, starting to provide in a systematic way metrics which measure impact on blogs and all these other kinds of things. So once you start to measure, people start to respond. There's a time lag, however. If there's really a big advantage to doing things in this way, if people are really building great tools, though, of course that to some extent compensates for that time lag. So it's 6 of one, half dozen of the other. That's not a very good answer, but I'd be interested to chat later. Okay, and I'm being told that is time.
Yeah, I'm sorry, but it's time. I have to announce that Henk de Vries' talk is cancelled and it's replaced by Peter Style from Coreboot. We will have more information in a few minutes.
Thank you all.
Yeah, the guy from Light is coming back in a second, so I'll ask him.
remain. Okay, we are continuing. Although this is a political part of HAR, since we have to cancel one of the talks, now we will have one technical talk replacing it. This is Peter Stuge from Sweden. He will be talking about Coreboot, which was previously known as Linux BIOS. It's BIOS replacement software for your machines. He is with the project for 8 years now, so I hope you like this talk.
All right.
Your mic.
Is this on?
Audio.
Okay. Hold on. Yeah, it's on. It's on now. Yep, here we go.
Okay, if you have problems, use this.
All right. So, can you all hear me? I don't know. It doesn't. No? Okay, I have to speak up. Oh, there we go. Perfect. Thank you very much. So, just to be perfectly clear, this is not the Henk de Vries talk. I was told that he canceled, and I offered to fill in with my Coreboot presentation last minute. So, this will be about Coreboot and not about the talk that Henk de Vries was going to give. I'm going to talk to you quickly about who I am. I'm going to talk a bit about Coreboot, some history of Coreboot, the competition that we're facing, the motivation for Coreboot. I'm going to talk about payloads because that's a big important concept in Coreboot. We've also developed a couple of auxiliary tools during the time that we've been working on Coreboot, and I'll mention those. I have sort of a demo. Unfortunately, I don't have demo hardware with me, but I'm going to do the next best thing and show you guys a video presentation or a clip of a previous presentation where I did have hardware with me. So it's almost like the real thing. I'm going to talk a bit about security, attack, defenses that can be relevant for Coreboot. Not right now, sorry, I have to call you back. Hello? Hi there, I'm up on stage at HAR giving a presentation right now, so I have to call you back. Can I do that? Thank you. Bye. Okay, these things happen. Security stuff, attacks, defenses. I'm going to sort of come to a conclusion, and then I have some thanks and links for you guys. Who am I? My name is Peter Stuge, you heard that already. I'm a self-employed consultant in southern Sweden. I do software, hardware, security work, everything from microcontrollers to databases and systems design and whatever. And I also have an interest in security and try to help out there whenever I can. I discovered Coreboot in 2001 when I was working as a developer for a hardware company. We were working on developing a set-top box for viewing TV over IP. And this was a PC platform. It was a custom mainboard, but it was still a pretty plain standard PC system. So, of course, we needed a BIOS. We needed something to help us get the operating system running. And I discovered Coreboot, or Linux BIOS, as it was called back then. And I thought, this is a really cool project. We should use this in our product. Unfortunately, we chose another firmware, but I stayed with the project because I really liked the idea. And I like to think that I stayed mostly silent watching for a couple of years, but apparently there are some people saying that I was pretty active on the mailing list already back in the start. Anyway, in 2006, there was a developer meeting in Hamburg. And that's not really far from southern Sweden, so I decided to drive down and get together with all the other Coreboot developers.
I had just installed coreboot on a small via EPIA mainboard in my car, and I talked a little bit about my experience from that as a new user in the project, or a newcomer, because I thought there were some usability issues, or usability issues even for developers when trying to implement coreboot. It was kind of tricky, so I wanted to work on that a bit. I took a great part in the design of version 3. I talked a lot about how I would like things to work, improving the design of version 2 wherever possible. We started out designing version 3 at this developer meeting in Hamburg. I've also done a lot of work on Flash ROM, which is one of the utilities that I'm going to talk about in a bit. Likewise, MSR tool, which is a debugging utility. I've hacked a bit on Philo, a bootloader that goes well with coreboot. I've done some K8, some of the K8 things in coreboot. And I tried to do user support and marketing of coreboot as well, because that's important too. So some history for coreboot. The project first started in 1999, so this is a 10-year anniversary. This year is a 10-year anniversary. It was called version 1. The repository name was FreeBIOS. It was the first try. It was really, really simple, maybe 5 lines of code. The truth is, it turned out not to work so great with just that little code. It needs to do a bit more. It supported roughly 50 boards eventually, and it still runs in some systems that are deployed. About 2001, version 2 came about, and it had a bit more structure, a little bit better structure than the first attempt. Not so much of a hack. It supports some 140 mainboards right now. And in 2006, we started coreboot version 3 at the meeting in Hamburg. A lot better structure, I think, not such a bad hack. It doesn't have that many mainboards supported, and by now it's actually sort of stopped. Development has stopped there, but we did a lot of nice things in version 3, and we're trying to move them back into version 2. So version 2 remains the popular version and the main repository for the project. But we're moving stuff in from version 3. Most notably, maybe lately, is kconfig. So version 2 previously used a proprietary, well, not closed source, but still our own configuration file format. And turns out that's not really so easy to work with. And for version 3, I really pushed kconfig, the configuration system which is used for the Linux kernel. So that's in version 3, and it's also on its way back into version 2 right now. So I think that's really good. We managed to do design testing on a handful, several embedded x86 mainboards using the G.LX CPU from AMD. So what is coreboot? I think you're all brave for being here because the program was changed a little bit last minute and there wasn't a lot of detail, so I'm happy to see you guys here. Coreboot is a BIOS replacement, an open source BIOS replacement for PCs. So an x86 firmware. And looking at the BIOS, what does the BIOS do? It has 2 tasks. The BIOS does hardware initialization. First off, it starts up the system so that software can run on it and can use all parts of the system. Then the BIOS goes on to start the operating system. It loads the master boot record, or it reads the master boot record from hard drive. It might start up a bootloader. Maybe you're using Lilo or Grub. Or it can read a CD-ROM or a USB memory stick. And the BIOS also provided interrupt services. That's a software API for applications running in the system to do basic input-output. That's what the acronym is stand for. In reality, no one is using these interrupt services anymore. All the operating systems nowadays, they have their own drivers for every piece of hardware. So the interrupt services have become pretty much obsolete. Only DOS is really using them, and the very early stages of some bootloaders also use them. So we have hardware in it, and we have the operating system starting. Why do we even look at core boot? What's the purpose of this? Why are we doing this? There's a number of reasons. First of all, it's open source, and none of the traditional PC firmware vendors have open source products. So that's a big deal. Second of all is sort of related to the open source fact. The people who started working on core boots back in '99, that was the Los Alamos National Laboratory in the US. They were building a supercomputer cluster with a couple of thousand machines. And they really didn't want the keyboard error, press F1 to continue message on their 4,000 machine cluster. So they did the only natural thing, and they started an open source firmware project. Also, I think another reason why core boot is really relevant is that we see a number of things coming up now lately, the last few years, in the security research field, where there are issues and risks that I'm going to mention a bit later with the firmware. And because we don't really know what's going on there, and we don't have a full insight into this execution stage, there's a lot of stuff that can be going on there, and that's not really so nice. So the BIOS doesn't work really now the way it used to. I mentioned these software interrupts. They really worked as an API. So the operating system and applications would call into the BIOS to do simple I/O, like output characters on the screen or to the serial port, or maybe read from the keyboard or whatever. And this was how the system ran, and it's not really different from an operating system, or not different from today, just that today the operating system has all the drivers and the BIOS isn't really involved at all. So this changed when the first laptop came about. The first PC laptop, it had a lid so you could close it, and when the boss closed the laptop lid, he of course wanted it to shut down automatically. So there came APM. That was the first power management technology used in PCs. When you close the lid, the processor would switch into a new execution mode called system management mode, and do a shutdown, a clean shutdown of the system, sort of pause everything that's going on in the system, and then power off, so that you could just close the lid and pack the laptop in your bag. So how many of you guys know about system management mode in here? Okay, maybe 10 out of, say, 80, 90? That's good. It's good. System management mode, as I said, it's a new execution mode introduced in the 386 SL processor. So this is a really old technology, almost 20 years old. When the processor switches into system management mode, it really freezes time. So whatever is happening in the computer is completely stopped, and no changes are allowed. All the state is saved. Once in system management mode, the processor can execute some small functions and really do whatever it wants to, because the normal system is completely stopped. So all state is saved, and a pre-configured system management mode handler is executed. And there was also an electrical signal added to the processor, so a new pin, a new interrupt pin, which is, of course, what was used for signaling that the lid was closed. So when you close the lid, this pin wiggles on the CPU, and the CPU switches, pauses whatever is running, the operating system, switches into system management mode, which will do hibernation, save state to hard drive or to memory, and power off. It's not only this new interrupt signal, though. System management mode can also be invoked by SMI traps. And these SMI traps, they're really a software filter. So you set up a number of rules where accesses to particular RAM locations, so particular addresses in RAM, or particular I/O ports, I/O addresses, will in fact trigger this system management mode. And using this technology, you can quite easily virtualize hardware. Because, for example, the PCI bus is really, it runs really completely off of 2 I/O ports, or, well, 8 I/O ports, 8 I/O addresses. And if you hook these I/O addresses to go into system management mode, an operating system trying to scan the PCI bus could, when it reaches a special point, be moved into system management mode, or the system switches into system management mode, and there's a system management mode handler which replies just as if there was actually a PCI card plugged in. But in fact, it's just a virtual PCI card running in system management mode. AMD Geode, the Geode series, which is what we were using in the set-top box, and also something that's been well supported throughout the history of Linux BIOS and core boot, because AMD really help us out a lot. The Geode platform, it works like a PC, but it's really a new architecture, and it uses system management mode to virtualize PCI devices, like I just described. Also, any PC that you might have that supports USB keyboards and USB storage in the BIOS will be using system management mode, especially for the keyboard emulation. If you have, if you're able to plug a USB keyboard in and still type stuff on that to your bootloader, then you can know that your USB BIOS, or your USB BIOS is running some system management mode handler. The PS2 keyboard is also using I/O ports, so when the bootloader tries to talk to the PS2 keyboard on these I/O ports, in fact it triggers system management mode, which will communicate over USB instead, and then return a result just as if there was really a PS2 keyboard. APM was the start, the first try at some kind of power management, power awareness in PCs. After that came ACPI. So ACPI is the Advanced Configuration and Power Interface Specification, conjured up by friends at Hewlett-Packard, Intel, Microsoft, Phoenix, the major BIOS vendor, and Toshiba. The revision 3 document, which I've had access to, or which I've found, is from 2006 and some 600 pages. Among other things, for the configuration part is pretty simple. It specifies tables of what hardware is in the system, how much memory do you have, etc., etc. Nothing really spectacular. For the power part, it specifies a virtual machine which has its own bytecode. And this virtual machine runs in your BIOS. So outside the security controls of your operating system. Is it really outside the operating system? Yeah, at first they implemented it that way, but it turned out to be way too slow. The performance hit was, I've heard the number 5% performance lost because the ACPI virtual machine was implemented all in the BIOS. I'm sorry, I just remembered I forgot to plug my laptop in. There we go. This virtual machine, it moved into the operating system because of this performance hit. It was just unbearable to have 5% gone. And Linux started doing this in 2001. I've seen the number 90,000 lines of code in the Linux kernel to implement the ACPI virtual machine at present. And the good, or the fun, interesting part is that it still operates outside the operating system security model. It's how ACPI was designed to work, how it was designed to run, and it's the only way it really can work. So, yeah. And who is providing this ACPI bytecode? Well, it's in your BIOS, so it comes from the BIOS vendor. Okay, looking around, what's out there in this field? For the PC, there's really two options. There's BIOS. There are a few BIOS vendors left. Really only two big ones. That's Phoenix and that's AMI. They bought everyone else. It started out in 1978 with a tape player I/O abstraction. So there were two brands of tape machines, and there were a couple of different PCs. And in order to talk to the different tape drives, you had to drive them a bit differently. So the BIOS was implemented to abstract the differences. And that was really all it did to bootstrap the system. In 2009, it's an API with well over 100 function calls, a lot of stuff that can be done if you ask the BIOS, mostly real mode code. I listened to a presentation by one of the commercial BIOS vendors, and they said that, well, our code base, it has 4,300 files in it, all assembler files. But they said it's modular, so it's really easy to work with. I don't know. I would probably prefer a bit fewer files myself. That's the BIOS. It works the way it always has. Then there's the new guy. That's EFI. Originally started by Intel. It's almost an operating system. It has its own network stack. It has support for timers. It's really modular compared to the BIOS, which is just one big lump. It's possible to download a development kit called TianoCore from the web. It's BSD licensed, about 250 megabytes, and compare that with Linux, which is maybe 50 megabytes. EFI is claimed to be open. And in fact, I've heard that the BIOS vendors, they were really scared of EFI when it was first started by Intel, because they thought, oh, okay, now open source firmware, now we're not going to have any market for our products anymore. But in fact, the open part of EFI is really just the foundation, and the BIOS vendors, they're all using that foundation, and they're adding building blocks onto that. So they still have their products. That worked out well for them, but it's not so nice for us because they make all their products closed. Because it's BSD licensed, that's okay to do. But still, I would prefer an open alternative. That's it on the PC, and of course there's Coreboot. There are some related projects. Maybe you've heard about Grub and Lilo. I guess many of you are using either of them. They are bootloaders, and they relate to this field, but they run after the firmware is done. So first we have Coreboot or BIOS or EFI, and then we move to a bootloader, which is started by the BIOS or the firmware, and the bootloader is responsible for starting up the operating system. There are some other options like Redboot, U-Boot, and PMON. And there's also PMON 2000 for the Lungson processor and some MIPS processors, but they're really not so much for x86 architecture. They're more popular. I know U-Boot can be made to run on x86, and maybe someone is using it already, but other than that, they're all for smaller systems. Otherwise, they have the same function. They initialize the hardware, and they get the operating system started. So I said Coreboot is a BIOS replacement. And we talked a bit about how the BIOS works, how it's split into the hardware init and the operating system start. And Coreboot does things differently. I think much better and at least very differently. Coreboot only does the first part, the hardware initialization, and then Coreboot is finished. Coreboot doesn't run anymore. After the hardware initialization, there's a separate program which has to take over and do whatever should come next in this system. And we call that program a payload. Coreboot, the payload with Coreboot, it can do whatever it wants. It can start an operating system. It can be a utility, some kind of application. There's really no limit to what can be done in the payloads. You are the only software running in the system. You have full control. Many times it is a bootloader because you want to maybe start an operating system. Core boot and the payload, we put those two together in the core boot build process, and then the result is flashed into the BIOS flash chip on the main board. So out with the BIOS and enter core boot and payload. What are all these payloads then, or what payload